Hello everyone. My name is Ramakrishna Sen from Dual Degree second year. Today I'll be taking a small talk on the working of speakers and how they can be designed specifically. The whole talk is divided into four sections. Mainly the basic overview. We'll start off with that. With that, we'll move on to the analogy, and that is the core part of this talk. In that analogy, we'll be talking about how the speakers can be treated as a system of its own, and that system can be compared with other mechanical systems present, mainly the damping system. Once we are through with that, we can move on to the construction. Um, the construction will be a very general construction in that sense, and to control what we require as an application, we'll be focusing on the design parameters as well. So let's begin with the overview. So, a loudspeaker converts electrical signals into sound waves. So, how does it do that? We can do that because we have something called a Lorentz force, which has control over the current through a magnetic field. Which gives you the force over whenever there's a current carrying conductor through a magnetic field. Um, So this equation is heavily used, although we won't be using it throughout the talk. This is heavily the background for what happens behind the scenes within an electric loudspeaker. Uh, so this is a general block diagram for the system where there will be an input, there will be an output, and there will be a controller, right? The controller is mainly comprised of an amplifier, mainly the class A amplifiers. And why does it have an amplifier in it? Is pretty obvious because you need to amplify the input signals through the microphone. The microphone is the same as a loudspeaker in the sense that the construction is same, but the controller inside the microphone is different. Just to be one step ahead of the talk, microphone has a sensing element and a solenoid element, right? We will talk more about the solenoid element throughout the story, throughout this session. Um, so yeah, it has a sensing element here. In case of the loudspeaker, there is no sensing element anymore. Uh, it still has a solenoid, but there's no sensing element. This sensing element is the key. This is the controlling element right now. So the sensing element is useful because it's a sensor, and the controlling element is useful because it's an actuator. We'll speak more about this. So I just wanted to give you this idea about the similarity between a microphone and a loudspeaker. So yeah, so before we actually do get into the nitty-gritties of this, we will look at the circuit model. The circuit model can be either mathematically intensive or we can just move on to logically representing the circuit. Since there is no capacitive elements present inside, we can just simply treat the impedance, the net impedance of a loudspeaker as the DC resistance plus its uh, the reactive impedance. So through that, we can actually get into some interesting conclusions, namely the control over frequency. So we can actually have an audio output, right, with a higher frequency or a lower frequency, right? So we can see that in case of a higher frequency, the impedance increases, right? And in case of a lower frequency, the impedance decreases. It is easier for us to create lower impedance signals than to create higher impedance signals, right? So this is what we are discussing, the effects of the impedance on loudspeaker performance. So since the reactance omega L is small, the impedance is dominated by R, hence allowing more current to flow. And at higher frequencies, this same increases, reducing the current, and hence the force applied on the diagram. So this is important because an actuator requires more current rather than more voltage. So since if the current is reduced, the force applied on the diaphragm is reduced. So the frequency has a very limited high frequency response. So this is the conclusion for that um, that above discussed topic. This is the frequency dependent behavior explains why many loudspeakers are efficient at reproducing low frequency sounds while struggling at high frequency sounds. Um, We will actually work more on that in the design part of that, design part of the session. So now to the mechanical equivalent model. Uh, the main one I want to compare it is the spring mass damper system. Uh, it is a very common system wherein there's a damping oscillation occurring with a spring mass. So instead of a spring mass, I would like to compare the elements of the spring mass system with the loudspeaker model. So M, which was the mass of the spring, right? If this was to be the spring, this was M, right? I'm interested to compare this with the moving parts, right? So in case of a loudspeaker, that would be the diaphragm, right? I'm getting the spelling wrong, but yeah, that would be the diaphragm. The diaphragm is the moving part of this loudspeaker, and we are comparing with that. This can also be treated as the inertia of the system, right? So inertia is the resistance to change, the measure of resistance to change. So diaphragm, the more thick material you use for the diaphragm, the more resistant it would be to change, and more harder it would be to create vibrations, right? So generally, it's a very good practice to create a thin membrane for the diaphragm, but it's just a physical part of the system. It's based on experience rather than control. Um, Next is the constant B, which is a damping coefficient. The damping coefficient actually controls the response of the system. And by response, I mean how fast the vibrations die out. So by dying out vibrations, I mean there are two consecutive audio frequencies you need to display or you need to send out as an output in the loudspeaker system. So how quickly can you do that? What is the time delay between those is the one I'm focusing on. So if there's a response which has a very high damping coefficient, this means that the response will die out quicker, which means you can have the next output faster, right? Next is the K, which is the stiffness of the system, which is how perceptible is the system to change, right? Um, in general, this system of the damping spring mass system is governed by this differential equation given, the second order damping differential equation. But mind that this is not the same. So this is not the same for the loudspeaker system, right? But why do we use it? Because the approximations are good enough, right? Since the approximations are good enough, we might use it interchangeably or to predict the behavior of the loudspeaker. And there are also some topics, advanced levels like FEA, which is finite element analysis. And we can use softwares like ANSYS, etc., to model those systems more efficiently. But that's not the part of this talk, so we'll skim through it. Since we also talked about frequencies, there's something called resonance frequency, and resonant frequency is the frequency at which the performance of the loudspeaker is at its peak. So the graph is something like this. This is the frequency, and this is the performance. Performance is generally given by the variable eta, right? The variables, the theoretically frequency of it is given by 1 by 2 pi k root of k by m, which is actually an approximation again because it is taken from the damping coefficient, damping spring mass system, but it also has a similar frequency output. The quality factor of it is the quality factor Q. This describes the damping of the system. So this actually means how sharp the output of the or the what is the quality of the output from the audio system, which you actually want to take up. Right. So after this, we can move on to the mechanical analogy. So this is what the analogy we talked about right now. We will actually try to uh, simplify that over here. So assume that this inductor here, which is mentioned to be a solenoid, and there's a constant voltage source. So this is the solenoid, let's say, and it's a constant in a constant voltage source, and there's a permanent magnet here with the terminals mentioned. If we have a DC voltage applied here, then there's some pulse generated, and there'll be some north south present on the solenoid as well. So once that is there, there's either an attraction or there's a pull based on what is the polarity of the input signals, right? Now, what if we change this to a sinusoidal or an AC source, wherein before it was a DC, now it was an AC source. If it is an AC source, then there's not just one, but there's attraction as well as repulsion. Don't you think? So there's a pull and a push force present, which is actually making this coil to move up and down. So if we keep this coil free and this magnet rigid, right? So you can very well see why this element will start to oscillate up and down, right? So this same system is very useful to create mechanical vibrations, right? Since we are able to control this mechanical vibrations using input current I. So after varying this input current, change in input current, I can vary the vibrations here. So what's my intention to do that is I will now control the I such that the vibrations produced will exactly replicate the input sound or the input frequency I have just given as an input to the microphones. Um, you can also do that in case of tape recorders, where there's some audio tape where a frequency of digits are there, and you want to replicate that. So you can also do that by controlling. All you need to do is now control the input signal line, right? So yeah, so now we'll actually move on to the different construction steps and what are the different elements present inside. Briefly speaking, there's something called the voice coil, which is right here, this part, right? There's a dust cap, right? Dust cap, membrane, and the beading. These are the physical part of the loudspeaker design. Then there's something called the frame, right? So all of these are the rigid portions. The main part of it is the solenoid here, which will be added, and which is included inside the voice coil, right? So the voice coil is both the permanent magnet plus the solenoid. This is this is what comprises inside the voice coil. So yeah, so as mentioned before, this is a general purpose G12T audio speaker, which is very commonly used in guitars. Uh, Not anymore, but it was at some point of time. So yeah, so the gaps are exaggerated here just to show how the difference between them. But this is not as far away as you think. The gaps are so tiny that you can actually fill them and they'll become one magnet as a whole. But for simplicity and for ease of understanding, we'll keep that different. On top of this, we will set up the solenoid and we will give it two terminals to operate the AC signal with, right? So yeah, this was what I was talking about in the previous slide. Now, once we do that, we will add a frame, which is again the rigid part of the system. And on top of that frame, we will add the cone or the diaphragm. Now, this diaphragm is the one responsible for creating the oscillations. Now, you may see why. And the design part of this is actually very crucial because the way you place these diaphragms are are also critical. There are cases or instances of destructive interference when the diaphragms are placed wrong. So that is part of the design engineers to figure out what is the correct orientation for the diaphragms so that there is always a constructive interference rather than destructive, right? So it is known that during destructive interference there are blind spots present inside, so which we actually want to avoid. Uh, yeah. So a dust cap is just this portion of this audio speaker. A dust cap is the one providing any external force from coming inside and actually tampering with the signal, audio output signal, because this is the one crucial and this has a very small magnitude of change. Now, if that change is also altered, then the actual audio produced by the loudspeaker might get altered as well. So you want to prevent that as much as possible, which is why there's a dust cap present, right? So since all of these are done, we can actually now move on to the design parameters. And why is the design parameter required is a very big question. The design parameters are required because audio devices, um, our main goal is to control audio devices, right? Specifically the output bit. Now, the audio devices might come into a plethora of use cases. The very first obvious one will be a loudspeaker, right? So you want one very small input wave into a very large output wave, right? That will be the job of a loudspeaker. Next, you might want it to be used in earphones, right? Earphones are also one type of an audio device, right? Audio output device. So wherein the input might be low, the output might be required to be even lower, right? But you want to replicate that input as an output. You just are changing the amplitude, right? Those will be earphones. Then some similar use cases would be headphones and etc. Right? There's lots of use cases. So to change that, you need to change the design parameters. You need different approaches to design those stuff, and which is actually given very specifically in a comprehensive parameter list called the TS list. It is the name of two scientists, Thiel and Small, and they have given through the parameters of this. Now, since this is a very advanced level topic, we will only go through its details briefly. So yeah, the Thiel small parameters are just a set of electromechanical characteristics that define the behavior of the loudspeaker driver. Um, Design optimization, etc., will be taken care of by taking care of these variables, right? So very first one, we will talk about the resonant frequency. So this is just the compliance. So this is the frequency at which the mechanical mass, speaker's mechanical mass and compliance resonate, right? What does that mean? This means that at this frequency, the speaker will operate the best, right? Speaker's operation frequency. Then there's equivalent volume. So remember I told you about the dust cap preventing any external force from coming in, right? This same thing we are doing. Uh, this same measure, the measure of any external forces present inside, is given by the term PAS, which is equivalent volume. The Q factor, as measured in the previous slide, is just the same, the overall damping of the loudspeaker, right? The mechanical compliance is the ability of the speaker suspension to move in response to an applied force. Then there's damping. So damping is again the value K, which was used in the analogy, and it is given in a DC damping, basically. So the DC resistance of the voice coil affecting the efficiency and also the damping, right? So these were the very few discussions which we made on these small parameters, and our overall goal was to talk more about the construction rather than the these small parameters. I would also want to add one small topic over this, which is the similarity, right? The similarity of microphones mic to the loudspeaker. So as discussed, I'm just speaking on the general skeleton of it. As I said, the microphone was also a solenoid tied to a permanent magnet, and as is the loudspeaker. So I'll just draw that quickly and put another north and south here, north and south here. What was the difference between the microphone and the loudspeaker was the controlling element, right? There's a controller, right? There's a controller for a loudspeaker, and there's a sensor for a microphone. Now, if I am able to move, if I'm able to generate movements, then I will need a controller. I have an AC signal, and this is able to generate movements in the magnet, right? And once it generates movement, I'm able to generate audio frequency. Now, if it's the same, I'm able to move this solenoid using my audio frequency, right? If I'm able to do that, then I'm able to generate force using Lenz's law, right? You can recall, we can do that using Lenz's law, which says that in a magnetic field, if there is change in flux, right? change in flux. This gives you what? This gives you I. So basically, it's given by uh, minus n d phi by dt, right? So E is given by n d phi by dt. So using this, we can actually, if we are able to generate or sense what is the current, right? Like an ammeter of sorts. We are able to measure the AC ammeter, the AC current through this coil. Then we will be able to replicate that using like what? Using a signal, right? Into a signal, if we can replicate that, and then send that signal again back to the controller to amplify that sound, or use that as an event, right? So yeah, so that actually marks the end of this talk. Thank you so much for following through.